Okay, part T, it says, hence show that the long-term transition matrix T to the infinity is given by this. Okay, so it's 6 marks, so we've got some work to do. And guys, it says show that, so you have to kind of put down all the steps. So we have this situation. We have this m to the n equals p times t to the n times p to the minus 1. It's t though, it's not m, so it's t to the n. And our transition matrix is, our t is given by this, where p is this that we calculated in the previous part. D is the diagonal matrix of eigenvalues, and I'll show you that in a second, but these are the eigenvalues 0.915 and 1, and these are the corresponding eigenvectors. P minus 1 is something I do want to get right now. I'm going to get P minus 1 here. To get the inverse of 2 by 2, hopefully remember, it's 1 over the determinant, which is this times this minus this times this, which is 7 minus negative 10, and minus a negative is a plus, so it's 1 over 17. And then we swap these two, 7 and 1, and change the sign of these two, negative 10 and 1. So that's P minus 1. So our P, I'm going to write all this out, is 1 minus 1, 10, 7. That's P. Our D is the diagonal matrix, which is 0.9150. This is a diagonal matrix, 0, 0 there and there, and 1. Now this is a diagonal matrix of the eigenvalues. What's important, guys, is if this is the eigenvector 1 minus 1, that the first eigenvalue in this matrix is the corresponding one. So look, the 1 minus 1, his eigenvalue is 0.915. The 10, 7, his eigenvalue is the 1, hence the 1 over here. Okay, now it's this matrix to the power of n, but the nice thing about a diagonal matrix is I can just put the n here and here. And then I'm going to multiply by this, by 1 over 17 times 7, 1, negative 10, 1. Okay, now I have 6 marks, guys. I have some work to do. I have to show exactly what's happening. Now the key is I have to say that as t approaches infinity, so it's when t is getting super duper big, you can't just sub in like 1,000 and show that if you sub in 1,000, it's pretty close to 10 over 17, 7 over 17. You have to show why this is the case. So if n approaches infinity, then this matrix 0.915001 to the power of n, this has to approach 0, 0, 0, 1. This is the most important step of the whole part of the question, because what happens when you do 0.915 to the power of infinity? Well, it just goes to 0. It's like the common ratio of a geometric sequence. We'll just do it to the power of 100, and you'll see it just gets super duper small, because you're basically getting 90% of 90% of 90% of 90%, and you just keep going forever. So it very quickly becomes 0. So this becomes 0, this becomes 0, this is 0, and 1 to the power of infinity is just 1. So this becomes 0, 0, 0, 1. Therefore, I can say t to the power of infinity is equal to 1, negative 1, 10, 7 times, instead of this, I'm going to put 0, 0, 0, 1 times 1 over 17 times 7, 1, negative 10, 1. And when I do all this on my calculator, hopefully we will get exactly what we said we'd get. So let's just do it. Menu, matrix and vector, create matrix 2 by 2. So 1, negative 1, 10, 7 times another matrix and another 2 by 2, 0, 0, 0, 1, then times 1 over 17 And then finally times another matrix, which is 7, 1, 1, negative 10. And I get what they wanted. So it's 10 over 17. Now, obviously, you didn't even have to do that calculation if you were confident that you were right. But they don't expect you to multiply it all out by hand, although you could. But this on the calculator gives me what I want. So I've shown it. Okay, that's part D.